Now in this example, we want to analyze the radiation between some surfaces that are not black bodies. I do advise you to pause the video, read the example for yourself and try to summarize it, and then unpause the video and see if you got it right. If you have unpaused now, I'm going to go over the problem. In manufacturing, the special coating on a curved solar absorber surface of area A2, and that's this absorber here, is cured by exposing it to an infrared heater of width 1 meter. This is the heater on the bottom. The absorber and the heater are each of length 10 meters and are separated by distance of h1 meter. So basically everything about the geometry of the system is given. The upper surface of the absorber and the lower surface of the heater are insulated. That is, there's no heat loss through, for example, conduction. The heater is at 1000 kelvins and its emissivity is at 0.9. Of course, you want the heater to be at a higher temperature if you're radiating heat from the heater to another surface, and the other surface is sitting at 600 degrees Kelvin and has the emissivity of 0.5. The system is in a large room whose walls are at 300 degrees Kelvin. When we talk about a large room, remember that large cavity at a given temperature. We generally consider large surfaces as black bodies. So the system is in a large room whose walls are at 300 degrees Kelvin. What is the net rate of heat transfer to the absorber surface? So we want to see how much radiation is this surface receiving. The very first thing that you have to do in problems like this is to categorize the different types of surfaces that you have. You can categorize them because their emissivities are different, because their temperatures are different, because some of them are black bodies and some of them are not. Now in a case here, I want you to think, what types of surfaces do we have? We have a heater surface, we also have an absorber surface. Their temperatures and emissivities are very different, and we also have the surroundings. All the surroundings on the left side, the right side, all the surroundings are sitting at 300 degrees Kelvin, and because the surroundings are large areas, I'm going to treat them like a black body. In other words, any radiation lost from the heater to the surroundings through the opening here and here is going to leave this space and not come back. In other words, those two surfaces on the sides, I can just consider them like imaginary surfaces, call them the surrounding surfaces, and assume that they're like black bodies, because any radiation towards them is not going to be reflected back. But they are at a very low temperature at 300 degrees Kelvin, so they do receive some radiation, some net radiation, or in other words, they do emit radiation at 300 degrees Kelvin. So now we're going through some steps, and I do advise you to follow these steps for any radiation analysis problem where you have surfaces that are not black bodies. Now here we have an absorber, we have a heater, and we have the surroundings, which are all the same. They're all at 300 degrees Kelvin, and I'm going to talk about the fact that we consider all of those to be like a black body. So I'm going to consider this area all at surroundings, and I'm going to call the heater surface 1. I'm going to call the absorber surface 2 and the surroundings surface 3. Now the radiosities for these would be J1, J2, and J3, as you can see in the bottom of this slide. We connect each radiosity node to each of the other radiosity nodes through the appropriate space resistance nodes, relations corresponding to radiation between surfaces. So we said before that the radiosities are related to one another through what we call the resistance, the geometrical resistance, or the resistance that takes into account the fact that different surfaces have different radiation towards one another and have different view factors. So I'm going to connect them . So I'm going to say that J1, J2, and J3 are connected, and I have some resistances that depend on the geometry of the surface and the way that these view one another, and that is going to be 1 over The one between J2 and J3 has the view factor between 2 and 3. So it's going to be A2 F23, or this resistance could be A3 F32. They should be the same based on one of the rules that we reviewed for the view factors. There's also a relation between J1 and J2. So I'm going to say this is 1 over A1 F12 or 1 over A2 F21. In the future slides, I'm just going to pick one of these, but at any time when I find that one view factor is easier to find than the other, I can just substitute with the other one. They are supposed to be the same. This one is going to be 1 over F13 by A1 or F31 by A3. So in step 3, we are connecting the black body emissive powers associated with the temperature of each surface to the radiosity nodes of each surface. The radiosity nodes, we've already set them up from the previous slide, J1, J2, and J3. And in between the radiosities, we did set up the resistance, the radiation resistance that depended on the geometry of the surfaces and their orientation towards one another, basically their view factor and their areas. Now we want to expand that and add the 3 nodes related to the black body potential for the 3 surfaces. So I'll have EB1 as Stefan-Boltzmann constant T1 to the power of 4, and I'll do the same for the other surfaces as well. For surface 2 I have EB2, and for surface 3 I have EB3. Now you can see that the resistance between your radiosity and your black body potential is given to you. We already went through this. It's 1 minus the epsilon of the surface and divided by epsilon of the surface area of the surface. So this, remember, was the resistance that depended on how this surface is very different, that is acting very different than a black body. So the more the surface is, for example, the more reflective it is, or the more it differs from a black body, you are going to have a larger resistance here. Now in the next step, we simplify the network, knowing that for black bodies, your radiosity is going to be equal to your emission from the black body. So of the 3 surfaces that I have, which are surface 1 for the heater, surface 2 for the absorber, and for the surroundings on the sides, I'm going to call them surface 3. Of the 3 surfaces that I have, surface 1 and 2 already have emissivities that are not 1. They're very obviously not black bodies. Surroundings, however, is considered like a black body because the areas are very large, and if you look at the opening, anything that goes, any radiation towards the openings, we're expecting it to be re-radiated through all the surrounding surfaces before it actually comes back to us. So in other words, any radiation towards the surroundings is not going to be reflected back. It's as if anything that goes past the surroundings line is going to be fully absorbed by whatever is out there. And also, we can also consider that all those surrounding areas are going to be emitting like a black body at 300 degrees Kelvin. So because of that, I'm going to assume that the surroundings is acting like a black body. So now I can say that the radiosity of J3 is going to be equal to the potential of the black body emission, or that is the Stefan-Boltzmann constant by the temperature of the surroundings to the power of 4. So this is how, in general, whenever you have any black body, you get rid of that node for the black body, you get rid of the resistance between the radiosity J and your EB node, and you just make your J equal to the EB value, which is your Stefan-Boltzmann constant and temperature to the power of 4. Now in the last step of this slide, we assume heat flow rates or adiabatic surface conditions. I'm going to use some of the things that I know from this problem. For example, I know that the net radiation is going to be from the heater towards the absorber because the heater is sitting at a higher temperature. So I'm going to assume that this is how the radiation is going to happen. Q1, this is heater providing more net radiation basically, and then you have Q2 going to the absorber, and then what happens here, you will have your Q3, which is the radiation lost to the surroundings. And based on this, I can make assumptions on how this radiation from J1 is going to go towards these two directions, and then I have this direction and this direction, and these are just my assumptions. If I make any mistakes in these assumptions, in a case where the problem is more complicated, then later I'm going to arrive at values that are negative or show me that I made a mistake. So it's okay to just make some assumptions and be consistent with them. It will be okay by the end of the problem. So in this step, I'm going to sum the currents at J node towards the unknown value that I'm looking to evaluate. The unknown value that we are looking to evaluate is the Q2 here. So I'll have to write the sum of the radiation in this node that is very close to that. And in order to evaluate that, I'll have to actually write the sum on here as well. So let's just write the sum of the currents that get into node 1 or J1. So for J1, I'll write it for J1. I'll be able to say that EB1 minus J1 divided by the resistance in between those, which is 1 minus epsilon 1 divided by epsilon 1A1, is equal to, between J1 and J2, J1 minus J2 and their resistance, which is 1 over A1 F12 plus J1 and J3, J1 minus J3, this is Q13, and this is Q12. So I'm writing for Q13, J1 minus J3, and I'll divide that by the resistance A1 F13. I can do the same for node 2 as well. So I'll write the balance for J2, and I'll be able to say that that's J1 minus J2 divided by 1 over A1 F12, which is equal to J2 minus EB2, which is my Q2 that I'm looking for, and divided by 1 minus epsilon 2 A2 plus J2 and J3, or in other words this Q23. This is the Q2. So Q2 and 3 would be J2 minus J3 divided by, find the resistance between these, which is A2 F2 3. Now how is this going to help me calculate the Q2 value? If you take a look on the node J2, this value is my Q2 value. Now in order for me to calculate this, I do need to have some values. For example, let's say I write the Q2 here separately. J2 minus EB2, which is actually, if I actually want to expand it, it's going to be, let's just expand it. Stefan-Boltzmann constant, T2, whoops, T2 to the power of 4 divided by 1 minus epsilon 2 A2. Do I know the emissivity of the surface? Yes, I do. Do I know the area of the surface? I do. Stefan-Boltzmann constant, I know. Temperature of the surface, I know. J2, I don't. So I do need to get my J2 to be able to find what I'm looking for. Now, J2, if you take a look at the above relations, if I'm looking at all the two relations here, I have J1 and J2 in the first relation, I have J1 and J2 in the second relation, and I also have J3, which is basically known to me because I said that J3 is actually equal to Stefan-Boltzmann constant T3 to the power 4. So it's basically all of this is gone. So J3, instead of J3 in this relation, I'm going to just say that this is Stefan-Boltzmann constant T3 to the power 4. So that is known. Same here, Stefan-Boltzmann constant T3 to the power 4, that is known. So I'm going to circle the things that are unknown. J1 is unknown. J2 is unknown. Again, J1 is unknown. J1, J2, J2. EB2 is my Stefan-Boltzmann constant to T to the power 2. So this is Stefan-Boltzmann constant T2 to the power 4. I know that one. How about the denominators? The areas are all known for me and the view factors are all unknown for me. So I'm going to plan the solution here. If I am able to calculate the view factors f12, f13, and f23, those are needs. So for here, needs f12, f13, and f23. If I'm able to get these view factors, then the only unknowns that I'll have in these two equations will be my J1 and J2. Then I will have two equations and two unknowns, one of which is my J2, which then I'll be able to use in here so that I can calculate my Q2. So here's my plan. First step, I'm going to calculate my F values, view factors, which are geometrical, but it has nothing to do with any of this calculation. So those can be done separately. So I'll calculate my view factors. Once I get those, I'll substitute them here to have two equations, two unknowns to get my J1 and J2. And then once I get my J1 and J2, I don't really need J1 because I only need J2 in order to calculate my Q2, which is what I want in this problem. So let's start that. So now here we want to calculate the view factors as we listed them in the previous slide, F12, F13, and F23. So the first view factor, and I probably think the easier one, is calculating F12. That is the view factor from the heater to the absorber. Now, from the heater to the absorber, I have a surface, a flat plate, going to a curved plate. We don't really have any relation for this in the tables, and I'm going to use some of what I can say based on just looking at the picture. The radiation from the heater to the absorber, or the portion of radiation from the heater to the absorber, is what the view factor is. So the portion of radiation to the absorber, if I were looking at this area here, should be equal to the portion of radiation that goes from heater to this imaginary area A'2. The same portion that goes to A'2 is the one that arrives at the absorber. So I can say that my F12 is equal to F1 A'2. And now, based on A'2, because this is actually a rectangular surface like this, another rectangular surface. Now I can use the figure in the book which shows the two rectangular plates with a distance L from one another, and I'll be able to use this figure in order to get the view factor between these two. Now if I take a look at the figure, I see that the view factor is on the left hand side on the vertical axis, and in order to calculate the view factor based on this figure, small figure that's shown here, I'll have to know what my x over L is here, and I'll have to know what my y over L is to pick one of these curves. So I'll have to calculate those first to be able to pick a point and then find the view factor from the correct curve. So let's get the x over L. What is x? Take a look here. This is your x, the width of the plate. So I'm going to call that 1 because in our problem it's 1 meters. And it's going to be divided by the distance of the two plates. So the distance in our problem is going to be 1, so that's going to be 1. This is where I'm sitting, and I'll just do this, but I don't know which curve to use for now. In order to know what curve to use, I'll have to use y over L to see which of these curves I'll be able to pick. So y is the length of the plates, which is 10 meters for our case, divided by the distance. This is y over L, and that should give me 10. That means I'll have to pick the second top curve, and that should bring me to around 0.39, or around 0.4 even. Around 0.39 is the view factor from 1 to A'2, 0.39. This is how we get the first view factor, just by using this figure. The second view factor is F13. So in order to get F13, I'm going to, the simplest rule of finding view factors sometimes is useful. Always think of that first. The simplest rule is F11 plus F12 plus F13 is equal to, all of these little portions are going to add up to 1. So F11 is the portion of radiation that arrives on itself. My heater is a flat plate. The radiation it doesn't see itself. It's not a curved surface, so I won't be able to have radiation from 1 to 1, so that's 0, and 1 to 2, I already found that, that's 0.39 plus F13, which is equal to 1. That makes my F13 equal to 0.61. So that's the second view factor that I got. And the third view factor is my F23. In order to calculate F23, I have to do a little bit of calculation because it's not as easy as these two. Let's see what I can use from what I know. I can say, based on calculation of F13, that F13 A1 is equal to A3 F31. And from there I can say, and to be honest, at this point I'm playing with these to be able to see if I can find some relation that gets me to F23. A1 is my area on the heater, which is going to be 1 meter by 10 the length, and then F13, I've already calculated that as 0.61. That should be equal to A3, which is the surrounding area, 1 by 10, and I have 2 of that on the two sides, F31. So from here I should be able to calculate F31 equal to 0.61, the 10s cancel, 0.61 divided by 2. I'll just keep it like that. So that's for F31, but that's still not enough to get me to F23. But I am thinking of F32, which is related to F23. So if I can calculate F32, then I'll be able to get F23 from there. So let's try to get that. We know from symmetry that F31 and F32 prime is going to be the same. 2 prime, remember, was the top surface here, and this is the bottom surface. From the surroundings, these two surfaces appear the same way. So I can say that from symmetry, my F31 is equal to F32 prime. So in other words, my F31 is, or F32 prime is going to be 0.61 divided by 2. So then I'll be able to use F32 prime. From F32 prime, I'll be able to calculate F32. So I'll be able to say that my F32 prime, whatever radiation, whatever portion of radiation that goes to 2 prime is the same portion that goes to 2. So then I'll be able to say that that's F32, which is basically that 0.61 divided by 2. So now I've got my F32, but I need F23. Take a look here. I need F23 and I have F32, and I know there's a relation between the two. A3 F32 should be equal to A2 F23. So area 3 is going to be my surroundings. That is 2 sides, 10 meters length, and the distance is 1. So that's my A3. F32, I already calculated that to be 0.61 divided by 2. And that should be equal to A2, which is, the actual A2 is given to me as 15 meters squared. So that's going to be 15 multiplied by F23. Now from here, I should be able to get my F23 equal to 0.41. So now I have it. I have 0.39 for F12. I have F13 as 0.61, and I have F23 as 0.41. So now let's go back to put these in the relations around nodes J1 and J2. Now that we've calculated our view factors, we will be able to substitute the view factors and the areas, everything that we know in these relations, in order to then calculate our J1 and J2 values. Or we were looking for J2 because J2 was related to the Q2 that we were looking for. If you remember, this was our Q2, and in order to get Q2, you need to have your J2. So let's get the values in the top relation 1 and relation 2. Stefan-Boltzmann constant is 5.67, 10 to the negative 8, multiplied by the temperature, T1 is 1000 Kelvin to the power 4 minus J1, this is my unknown. 1 minus emissivity, 1 is 0.9. And area 1 was 1 by 10. That's the first relation. J1 and J2, again, I don't know these. I'll leave them as is, but those are my only unknowns. 1 over A1 is 1 by 10, which becomes 10. And F12, I think I calculated it as 0.39 plus J1 minus Stefan-Boltzmann constant, 5.67 by 10 to the negative 8, and multiply that by temperature of the surroundings, which was at 300, I think, room temperature, to the power 4. So that is going to be divided to 1 over, again, area 1 was 10, 10 by 1 becomes 10, and F13 that I think we calculated as 0.61. So that's going to be the top relation. As you can see, the only unknowns are J1 and J2. If you actually put this in your calculator, you're going to get a very nice and clean relation. Something multiplied by J1 plus something multiplied by J2 is equal to a number. That's just a small relation. Right now it looks very huge, but if you put it in your calculator, it should become very small. For the second one, again, I'll be able to do 5.67 by 10 to the negative 8. Multiply that by T2, which is the temperature of the absorber, which is 600 to the power 4, minus J2. Divide that by 1 minus emissivity of the second surface is 0.5. Divide that by 0.5. Area 2, which was 15, is equal to J2 minus J1. I'll keep them because they're just unknowns. 1 divided by A1, F1 to A1 was 10, the heater area, and F12 was 0.39, plus J2, again unknown, minus 5.67 to 10 to the negative 8. That's my Stefan-Boltzmann constant. Multiply that by the room temperature, T3, at 4, and then divide that by 1 over area 2, which is 15, and multiply that by F23, which is 0.41. We calculated that last in the previous slide. So now I have two relations, two equations, two unknowns, and if I solve these two equations, two unknowns, J1 and J2. So if you actually solve this, you'll be able to arrive at J1 and J2 as, well, you know what, I'm not going to calculate J1 because we don't really need J1. All we needed was J2 in order to calculate our Q2. So I'm going to just calculate J2 from here. Of course, you'll be able to calculate J1 as well. 12,487 watts per square meters. That's my J2. I needed this J2 in order to be able to say that my Q2 on the lower right hand side of the slide, my Q2 is equal to my J2 minus Stefan-Boltzmann constant T2 to the power 2, or the potential of the black body emission, divided by emissivity 1 minus emissivity of the second surface divided by emissivity A2. Now that I have my J2, I'll be able to substitute it. 12,487 minus 5 by 10, 567 by 10 to the negative 8. And I'll multiply that by the temperature of my surface 2, which I have it available at 600. And, oh, whoops, this is to the power 4, by the way. So this is to the power 4, and I'll have this to the power 4. And then divide that by 1 minus emissivity of the second surface was 0.5. Divided by 0.5, and the area of the second surface was 15. This should give us Q2 equal to 77.1 kilowatts. And that's what we were looking for. If you wanted to, you could calculate everything else. Once you calculate J1 from these two equations, two unknowns, you'll be able to actually calculate J1 and anything, all the different flows, the radiation exchanges between the three nodes, you can actually calculate them.